Implicitly then we have dv dt will be pi over 3, and we have to do it with product rule. So that'll be 2r times the derivative of r with respect to time times h plus r squared dh dt. So there's the derivative of r squared with respect to time, and that's the derivative of h with respect to time. Okay, so then if we put this into our formula here, the volume is changing at pi over 3. The radius is 3 centimeters. It is changing at a rate of negative 0.1. And the height is changing at a rate of, the height is 8 centimeters. And it says the radius squared is going to be 3 centimeters squared. And the height is changing at a rate of negative 0.2. Okay, so we'll just have to plug this into our calculator here. We'll probably leave the pi over 3 alone, but let's punch in the middle of it. So that's going to be negative 6.6 and we can divide that by 3 pretty easily. We'll get negative 2.2 pi. And the units we're in, if it's moving in feet per second, well, I guess that's a little typo. We probably, just for consistency, right, our units should have been the same here, but or these should have been in centimeters then. But anyways, yeah, why don't we keep, that'd be a pretty gigantic cup. So the mistake was probably here. It's probably changing in centimeters per second, because that way we know our units for volume are centimeters cubed per second. So the volume is changing at that speed, which means the volume's decreasing because it's negative. And that should make sense again, because radius is shrinking, height is shrinking. So now we know how fast the volume is shrinking as well. If you are trying to determine what is that actually telling me, that tells you if you were to take a knife, right? We've cut a hole in the bottom of this cone. If we were to take a knife and at that very instant slice right across, the amount of water that's come out of it at that instant is negative 2.2 pi centimeters cubed per second. So that's, at that instant, that's how much water just left the cup. Okay. I think you'll find that it's, as the cup is fuller, there should be more volume coming out because all that gravity is forcing it out faster. Right? It's kind of like when you open a pop bottle that's been shaken, it sort of bursts on the way out, and then as the pressure in the bottle decreases, it goes out more slowly. Same thing with gravity, right? There's going to be more, I think there'll be more pushing it out than as it shrinks. But anyway, I'm not going to review the strategies as it's something we've talked about before. But let's apply those strategies and see what we can do. So here's the question. The picture's on there if you've printed your notes. Otherwise, you can copy it down quickly. How rapidly will fluid inside a vertical cylindrical tank drop if we pump the fluid out at a rate of 3 liters per minute? Or sorry, 3,000 liters per minute. Okay, so in this case, we have to think about the important questions here and what we can label. So the most important thing, I find students struggle the most in related rates because they can't tell me what they're trying to find. Can somebody use calculus talk to tell me what it is we're trying to find? Sure, Pete, go for it.
We're trying to find the rate of change of the
That's right. We're trying to find the rate of change in the height with respect to time. And that's this part here, what it says, you know, what's the rate at which it drops. So we want to know about the change in the height. And that's what I've written into the picture here. That's what we're looking for. When you do related rates, it sounds so simple, but this is the most important thing to start. What are you looking for? Because now that I know this is what I'm looking for, it gives me some hints as what I'm going to be needing to find in my problem. So we also have to figure out information that we have. The only other information we know is that 3,000 liters per minute is pumping out of this thing. So I've just labeled it in the picture here. That's how much is coming out. 3,000 liters per minute is falling out of this tank. So how do we relate? We have volume and we have height. How do we relate those together in a cylinder? That's the next step, is now that we know, we've got our information set out, we know what we're looking for, we have to relate them together. So usually it's a formula of some kind. So what do you think? How could we relate volume to the height? Yes? 2 pi r h. That's not quite the, I think that's, if it's all right. Volume formula. You probably already took a derivative of something. I don't know. But anyways.
Yeah, pi r squared.
Pi r squared h. So pi r squared is the surface area, right? And then the height, you multiply it by the height. So anyway, pi r squared h is what we have. And it looks like we're going to have to answer in terms of r then, because we don't have the information there. So we'll answer it and we'll leave it where r could be filled in. So to find dh dt, we're going to relate everybody by the derivative. So here's my derivative if I take it implicitly with respect to time. And this is what I'm looking for. This is what I wanted to solve for in my problem. So I'm going to rearrange that, and I'll have this here, and I can divide that out. So we get, I'll just divide it out here. So now I know what the change in the height is. It's this mammoth formula. And I know that the volume is negative 3,000. So at this point, without any other information, all I could put in is negative 3,000, take away 2 pi r dr dt over pi r squared. So that's not a good way to leave the question. Let's just say, possibly it was in the margin and I forgot to write it down. So let's just say that the radius was 5, and let's say the height was 10. And let's say the radius it's constant as the water level drops. So can anybody tell me what the rate of change is? Good. That's important, because then we have to figure out that this term would disappear. Because if the rate of change is 0, that whole thing would be gone. And then we'd end up with negative 3,000 over pi r squared. And again, since I've said, just to make it some closure, we've picked a radius of 5. It would be negative 3,000 over 25 pi. Okay. So sometimes when things appear like they're missing, we have to think a little bit more about what's going on. And in this case, we're not missing the rate of change in the radius. It's constant. Okay, a hot air balloon. So it's rising straight up, and it's tracked from 500 feet from the liftoff point. At the moment, the ranger's finder's elevation is pi over 4. It's increasing at 0.14 radians per minute. How fast is the balloon rising at that moment? So what we want to know is, you should be able to read that and interpret that as, you could call it height. Here it's labeled as y. We're trying to find what's the change in the height of this balloon with respect to time. Okay, that's always the first thing we should start with. The 500 feet from where it's observed, that's this part of the picture here. And this is pi over 4. And we know that the radius here, sorry, not the radians, the angle is changing at this rate here. So everything has now been labeled into my picture. I know what I'm looking for. The challenge is going to be, how do we relate these pieces together? So when you see trig, you have a few options, right? I mean, you might think Pythagoras. You might think SOHCAHTOA. What do you think we should do to relate these together? How come? Yeah, the pieces that we're dealing with are the opposite, adjacent, and an angle. So it makes sense to use tangent here. Okay, so tangent of theta is y over 500. So 500 tan theta is y. And that means, let's see here, 500 secant squared theta, d theta dt, is dy dt. So, I mean, I've practiced more than you have. I guess I'm a bigger nerd since I've practiced calculus longer. But I find the calculus is much easier. The difficult part for me is figuring out what am I looking for and how do I relate them in an equation. If I can get past that, I can usually beat the question. But I still find it challenging sometimes to pair those things up. So let's finish this one off. We can fill it in. That means with theta equal to pi over 4, and I've got it changing at 0.14 radians. I can then calculate what the speed that balloon is moving higher. So I end up with 140. And again, if you look at all the units that you're using here, we're in minutes when we're talking about our rate of change, and we're in feet for our units. So this balloon is going to be rising at 140 feet per minute. I'm going to have you do the next one by yourself, and I'll catch up to you. This is a police car approaching an intersection. So I'll let you read it through and see what you can work out. Again, you're going to want to start by thinking about what is it I'm looking for, and how can I relate all these pieces together with a formula. Okay, so I'm going to just get us set up, and then I'll give you a couple minutes in case you want to work out the derivative yourself. So everything is labeled in here, and we have this information about it being 0.8 miles to the east. So 0.8 miles to the east, that's right here, and 0.6 miles north, that's right here. And it says when the cruise, the distance is increasing at 20 miles per hour. So that's the length of this thing here. Increases 20 miles per hour. If the cruiser is moving at 60 miles per hour, and you'll notice that when it's labeled in the picture, how come there's a negative here? Yeah, it's dropping, right? According to the way we've set up this picture, it's going down. It should be a negative rate of change when it goes down. And similarly, the other one, which is headed east, to us, east is moving to the right, which means it's going to be getting positive, right? It's increasing. If it was negative, that means the car would be going in the opposite direction. All those orientations matter to us, so make sure you've accounted for them properly in your work. That's what we're trying to find, is how fast is the car going here. You know, the police officer points the radar gun at it, and the gun is not going to give the appropriate measure because the gun is going to be telling it this measurement, not the measurement of the actual car. So, I mean, I don't know that they programmed this stuff into the radar gun. I kind of assume they must, because otherwise, how can you give people tickets if your gun isn't working properly? So anyway, I think that's why most of the time, though, you find police on a radar, you know, on the side of the road, just stationary. But let's see here. We do have enough information to figure this out. How do we relate these pieces together in this information? Anybody come up with a formula? I'll give you a hint. He died a long time ago. He's Greek. Pythagoras, yeah. So if we consider this x, y, and then the diagonal, x squared plus y squared, and I'm going to use s for this because they have the derivative of s. So that's the equation that relates all three pieces together. Here's x, y, and then the slant. So if I take the derivative, that's 2x dx dt, 2y dy dt is 2s ds dt. And this is what I'm trying to find here. So I'm going to have to rearrange for dx dt. And I can divide this out, which means all those 2's would disappear as well. So now it's a matter of filling everything in, the information I have in the problem. So it says that, let's see here. I'm going to need to use these lengths and Pythagoras to find the length of s, because right here it says I need to know how long that is, the value of s. So s is the square root of 0.6 squared plus 0.8 squared, which, yes, conveniently is 1. And that means I can make my substitutions now. 1 times 20. That positive 20 means at that moment it's actually growing, the distance between the police officer and the car he's got his radar on. And then y, it says the distance for y is 0.6, and it's negative 60 because they're dropping at 60 miles per hour. And we have to divide it by x, which is 0.8. So this is going to give us the actual speed. If one day you find yourself in law enforcement and you end up doing this, I'm sure you'll win your case just because the judge will be so impressed with your calculus abilities. So it looks like they're going 70 miles per hour. And you'll notice that all of the signs that I said you needed to account for, this question won't work out properly unless it's been interpreted right. So 60 miles per hour, if that went in as a positive, this answer would not turn out properly. You'd also might find that 70 miles per hour, it should be positive when you get your answer because that's the direction they're headed. Okay, so last question. Water runs into a conical tank at a rate of 9 cubic feet per minute. The tank stands down and has a height of 10 feet and a base radius of 5 feet. How fast is the water level rising when the water is 6 feet deep? Okay. So in this one, how do we relate the radius to the height to the volume? Does anybody have a formula that'll work? Yeah, that's the one. Okay, so pi r squared h over 3, that's the volume for a cone. Now, what we'll do is differentiate with respect to time. So I'll get 2r dr dt plus, let's see, r squared dh dt. And now I have to be able to substitute all this stuff in. But you're going to notice there's probably we're going to have some problems here. If we do a quick survey now of what we have, you'll notice we don't know how fast the radius is changing. Say that one more time. Oh yeah, sorry, there should be a height right there. Thank you. You'll notice that we're missing the change in radius with respect to time. And we need to keep this one in here because that's what I'm looking for. How does the height change? So the problem is if I don't have that information, I have to be more creative. And that's why if you're used to this cone example, Does anybody know this? Just hands up. You know the strategy I'm about to show you because you remember it from before in the other lessons. Fair enough. But know that this is the most common. When you see a cone, there's probably like an 80% chance you're going to have to do this strategy. By leaving out one of those things, you have to rethink this problem by using similar shapes. If you look at the two triangles here, I'll do the big triangle in red, and I'll do the little triangle in green. Those two shapes are similar, so what I could write here is, for example, y over x is 10 over 5. And what I'm trying to get out of this problem here is I don't know this change of rate with respect to time. Or sorry, change in radius with respect to time. So I'm trying to remove x from the problem. So if I solve, x is going to be 5y over 10. Looks like a g. Let me change that. 5y over 10, which is y over 2. So in terms of the volume formula up here, that means the volume is pi y over 2 squared times y. So I did all that because I was able to eliminate the radius from the equation. If the radius is gone, I won't need to have the change in radius with respect to time. Okay? So I'll just warn you, there's not too many examples in related rates where you have to remove a variable, but this is by far the most common example of using the triangles for similar shapes. So let's finish up here then. We'll have the volume is going to be pi y cubed over 12. And even if you think about that, you should prefer to work with that formula. There's no product rule. It's a real simple polynomial. dv dt is going to then be 3 pi over 12 dy dt times y squared. So I'm going to rearrange it then and solve for how fast the height is changing. So that means dy dt is going to be the change in volume. Let's see here. 12 goes up. And 3, I'm running out of, hang on, it's going to disappear there. Running out of space here. 3 pi is on the bottom. And so is y squared. So I'll just simplify it while I'm waiting for you to finish copying that. Okay, so then if I substitute in the values we were given, dv dt is 9 cubic feet per minute. It's positive for a reason. It is definitely flowing in, so the volume is getting larger. And on the bottom I have pi and a height of, at that instant it's 6 feet deep. So it's going to be 6 squared. So that'll be 36 over 36 pi. So it's going to be 1 over pi. And my units, again, are in feet per minute. So I have 1 over pi feet per minute is how fast the height is increasing at that instant.